So it is my pleasure to welcome Bubba Knight to introduce the Osterberg lecturer. Bubba and I met when I was in my early 20s in the panhandle of Florida when we were lighting statnamic testing out over the water in some of the first tests that were conducted in the USA. It was a fantastic experience to rub shoulders with Bubba. Every time I do, Bubba tells me a story and I walk away and I think, oh my gosh, Bubba's an expert on that as well. So here I give you Bubba Knight.
Thank you, Matt. There are some that know me that have affectionately named those stories as Bubba-isms. They are what they are. It's Fugro Load Test's pleasure to sponsor the Osterberg's lectures in memory of George Osterberg. To that end, we've tried to select some of the best thinkers in the geotech world with the joint help of DFI, folks to stimulate our thought processes, stimulate our careers, in fact. So, and in fact, one of these Bubba-ism kind of stories, one day when I was in Florida DOT, my phone rang, gave it my southern hello, and a gentleman spoke and says, "This is Sam Paikowsky." I said, "Sam who? And how do you spell that?" So we shared some load test data that we had on projects from Florida DOT, and he improved our thinking with that. So to that end, Dr. Paikowsky is a professor at the University of Massachusetts, Lowell. Resided there for the past 30 years. He's the president of GeoDynamics, Inc. Close to 40 years of experience in the geotech-related consulting, research, and engineering projects. Expert in the field of deep foundations and reliability-based design, testing, analysis, and been involved in projects worldwide. Started out with a BS in civil engineering and a MS in geotechnical engineering from Technion Israel Institute of Technology, and a SD and a engineering, geotech engineering at MIT. Dr. Paikowsky, please, sir.
Thank you very much, and I'll start. My name is Sam Paikowsky. I'm associated with the University of Massachusetts at Lowell and associated with GeoDynamica. It's my honor to talk to you and receive the Osterberg lecture, memorial lecture. I'll say a few things about that. Just a few things about George Osterberg. He certainly was one of the giants of geotechnical engineering. Son of immigrants from Sweden that was involved years in teaching, and I'll show you in his age, our first drill shaft was done when he was 16, just to put it in perspective. Yet the guy developed what we call the O cell, bi-directional cell, and I think one thing to say about George Osterberg, that he was a nice human being, and I think that talks more than a lot of other things. He was a pleasant human being and a real fine person. I have to say a few things here. One of them is to the DFI Educational Trust that trusted me in giving the lecture. Thank you very much. Load Test that is sponsoring the Osterberg lectures. And I would say a few words about DFI. DFI emerges over the years as a leading deep foundation institution. And it has two major reasons, to my opinion. The first is the hard working of the individuals in the group, in the DFI group, all very dedicated and excellent workers. And in addition to that, all the people that volunteer their time and associated with DFI. There is another component which is extremely important that was recognized by DFI, and that's in deep foundation, more than any other area in engineering, civil engineering, and geotechnical engineering, the collaboration between the construction, the design, and the research is extremely important. It's vital. As a matter of fact, I don't think that you can have to design and get a good drilled foundation without a good contractor. And these things were recognized by DFI early on, and that's the core people that are making the group and very successful. Lastly, all the audience that are willing to share half an hour of their time with me, and hopefully those in the webinar as well. Regarding that, I want to say something. I had the kind of contemplation about what to present in the lecture. And there are a lot of high-end things that I do that could have answered actually the 3 lectures that we had in the first plenary session. For example, the solutions for dynamic analysis on plugged piles and why the gentleman that chose the result of the Seattle port came to the right conclusion that the signal matching showed him a lower result. We did that in the real solution and so on. I'll touch upon it, but it was not the topic that I chose. The second one was the concrete filled steel piles. And we actually worked for 3 years in Africa on a project that we developed it and tested it, including the shear between the concrete and the steel. You would have much enjoyed it. Well, I didn't choose that either. The third one was the issue of the calibration of load test, definitely the analysis of laterally loaded pile. We did that for a lot of piles, comparing test results, actual test results, to performance come from analysis. I will not show that, unfortunately. So what I did is we went back 30, 40 years and went to the fundamental of what is a load test, what is the capacity, and I hope it really unites, as much as there is no flashing things there, unites all the audience in understanding what we are doing in foundation. So I'll start with the background because as engineers, it's really important for us to know, to understand that we are a step in a long chain, and actually for us, we are very lucky that we are in the last 100 years or 70 years, see advances that people did not see for 12,000 years in a profession that we are dealing with. I'll also talk about the difficulties associated with that. Then I'll talk basically on something very fundamental. What the capacity of deep foundation? I'll talk about classic testing of load test, regular, up, down, what the principles, what we get as result, interpretation method, what we use, what should you use as failure criterion, and why. And then I'll go to related subjects that we very often don't grasp enough. For example, we are looking on load displacement. Very little we look on loading and settlement with time. What is the effect of a rate of the test within the static, not only dynamic? And what is of the settlement? Because there is a major claim of the issue of serviceability under vertical load. What's a typical settlement of a single pile and a group? And the last one, what's the effect of the size of the pile on our results? I have to put a couple of slides with what I'm really dealing most of the time, and that alternative methods of testing, limitations of down static load test, few slides on bidirectional. The wholesale can go with a lecture to the memory of Osterberg without showing Osterberg cell results, and some dynamic tests. So let me go with the background. First of all, we are part of a long-standing traditions that for 12,000 years we have evidence of people driving piles and build on piles. And this is actual. We have 4,000 years ago, and the Scots built islands based all on piles. We have evidence in writing by Herodotus, was the 4th century BC Greek writer that describes pile and pile driving. All the ancient people, the Egyptians, the Romans, the Chinese, the Mesopotamians, all relate to pile driving, and as a matter of fact, it didn't change over the years until about 100 and something years ago. They all drove timber upside down into the ground by manual labor for all these thousands and thousands of years. As a matter of fact, we have here Dutch friends, and if you go to the Queen's Palace in Amsterdam, it stands on 4,000 driven timber piles. The machines that they were used were not that simple. This is, for example, a Roman machine that pile drivers that were used in the Gallic War by Julius Caesar to build the bridges on the Rhine and on the Mosel. If you go to Trier in Germany today on the Mosel, There is still bridge that you can drive that is supported by timber piles that were built by the Romans. A long tradition. Without getting much into it, if you look into that, you essentially can see that there is a ram here made of timber. I don't know if you can see that or why. There is a ram here built of a ram made of wood backs for a big stone. It can be inclined. You can drive better piles, and it was working fantastic. The first person essentially that introduced mechanical driving was Otis Taft, the guy that Taft University in Massachusetts in Malden is named after, and he invented the steam pile driver, and it's not that long ago. Diesel hammers were invented after the Second World War. We're talking about 70, 80 years. We certainly within reach, especially the older piles. When we go to drilled foundation, it's much newer. This is a depiction of 1846, open caisson construction in Chicago, where essentially people dug by hand, cleaned it, brought it up in the buckets while maintaining pumping of the water. So if you look at that, it all started in the late 1800s due to large construction in parallel cities around the world, London, Chicago, and Detroit, and so on. And they all developed those drilled shaft foundation. The first person to start with a machine was look here for my, never mind, was Hugh Williams in 1931. Just put in perspective, Mr. Osterberg was 16 years old at that time. He built a very small machine for drilled foundation, anything that you would consider as serious today. So what we have done through this time, which is 70, 80 years, is enormous in pile driving and drilled foundations. We are sitting essentially on the top of an era of unbelievable development in construction and methodologies of building foundation. Well, the problems remain, however, over the years the same. We are having a limited ability to check the capacity and the integrity of an element that we put into the ground, regardless of how we put it, and of course some areas are better than the other. We have a very limited ability, and we have to struggle with that. As a result, we have uncertainty, uncertainty and conservatism that plagues the profession. When we started collecting databases about 25, 30 years ago, there were first databases really that could show any performance of analysis. For the first time, I remember giving a lecture in 2002 in Japan where they gathered all the people around the world that dealt with reliability. The lecturer before me came from Europe, and he said, we built all these wonderful Eurocode 7, however, we don't have any data to put it in. And then I showed up with hundreds of files that we analyzed. So uncertainty and conservatism really plagued the profession for years, and still is an issue that we are dealing today. At the end of the day, we put a member in the ground and want to make sure that it performs. So what we need is to assess pile capacity and integrity for optimal design, and the method is essentially testing method. We are looking for testing that provides resistance, capacity, and integrity along with the soil pile interaction, which we don't always get, and we'll talk about that. My major approach, as I said, will look into static and dynamic testing of deep foundation, but I'll concentrate mostly on the classic testing with limited reference to other testing methods, although that's my essentially most of the work that I started explaining in the lecture in these days, and I could certainly show you beautiful projects and very interesting stuff, but I chose to go to the basics. Let's go to the basics. What's the principle? First of all, the principle of the classic testing is up-down load test. Why is it up-down load test? Because we are simulating the loading that we have, they're all gravitational, and they are coming from up-down unless we have a pull-out or of that sort. It is, as a result, a benchmark for all the tests. Doesn't matter if we run dynamics, dynamics, or Osterberg. At the end of the day, we compare it to static load test as our benchmark, and therefore it's important for us to understand what is it exactly that we are doing and how it works. So we have the capacity, there's a basic for capacity discussion. I promise that I'll bring all the elementary stuff. So essentially, what is a test pile? What is a pile testing? The load test, we have a test pile in the ground, either driven or drilled. And we usually put, not usually, we put a jack on the top in order to apply load. And when we have an action, we need a reaction, and we put a reaction beam. And essentially, we put the action on the pile and the reaction against the beam. In order to hold the reaction, we are using either anchor piles or anchors that in the ground, which are being pulled out, or we are using a dead weight to provide the reaction. We measure top force and displacement. This is the classical load test that we are running. If we really want to learn more, we have two things to get. A, to bring that pile to failure, and second, to really measure the interaction between the soil and the pile, which we can do only if we measure local displacement by deltas. In the past, we used them also for force distribution, which is not yet easy or accurate. And for that purpose today, we are using strain gauges, and we have seen results of it earlier. ASTM provides us with all kind of arrangement. If you want to see the way it looks in real life, so that's the way it looks. You will have, for example, 4 H-piles with cross beams that will support the reaction beam, and we apply the load. If we want dead weight, we can do that, and I have some nice pictures from India where essentially sacks of sand are being used as dead weight. And one nice one that I decided to show is a long one that was done by us, in which actually we use the crane. I don't think OSHA would ever approve of that anytime, and I don't suggest you'll do it yourself, but that was a long time ago. And you can see we built a pit that looks more like an oil change in a garage, and then the crane that was in the background came forward, and we jacked against the crane as the reaction. Innovation is all over the place. What is the largest one that I ever was involved with? It was a 72-inch pile that I just mentioned earlier, in which we actually checked plugged piles, comparing dynamic testing on full scale. This was a 3,000-ton load test, static load test. You can see the two reaction beams crossing each other in order to get a huge moment of inertia at this huge loading, held by 40 tie-down anchors to a rock, and having 4 jacks. Each one is 900 tons. This is a massive load test that cost a few $1 million and was well justified. So from there, what is pile capacity? Well, we are looking at load and displacement as a settlement of the pile, and here you have an example on the right-hand side. And we ask ourselves, as a matter of fact, if we switched it 90 degrees, it would look like the stress-strain behavior of a regular material that you are used to in every material testing. We are looking on the load on horizontal axis and the displacement on the vertical axis, because that mimics the actual behavior of a pile. But if you twist it in 90 degrees, you essentially get the regular stress-strain behavior of materials. And we ask ourselves, what is the pile capacity? So we want to interpret those results, which are the basic results from the measurement on the top of the pile. And we first of all have to assume that we really arrived to failure, and we have a yield in which the load displacement can be examined. We're essentially looking in a location where we have excessive displacement under small increment increase in the load. Okay? We have displacement criteria that were used for years. 1 inch, 0.1b, all of them will do that. My friend Ben Selenius claims that our entire design of the pile should be essentially associated with a displacement criteria. And we'll talk a little bit about that too. There is shape of curve. When do we come to the point where we accelerate and we move from one regime to another regime of behavior, from elastic to more plastic behavior? And the interpretation often is not a unique value. For that result, I would like to look on the load test that I'm just showing you here. And I would like to see if we look on the load displacement behavior here and load displacement behavior here, you could guess probably where the capacity, what you would call capacity here. Probably in this case, it can be someplace here, and in this case, it will be someplace there. I don't ask you because of lack of time, but I'm sure that you would more or less agree. The point that I'm trying to bring is the same load test. Okay, it's the same data, just thrown on a different scale. So what I show you here is exactly the same load test, just thrown on a different scale. And the conclusion out of it, if you want to examine a load test, you have to look on a systematic scale that gives you. Those of you that remember Vesich many years ago, he came with the idea that if you'll take the scale such that the elastic compression line will end up in a 20 degrees, that will be a good scale to evaluate, and we use it systematically when you evaluate a load test. Something as simple like that, but extremely important. So just bear it in mind. From all the different analyses on driven piles, Davisson is certainly a popular one, and I'll explain. And pay attention, it's only driven piles. And essentially, Davisson came up with a very simple, not very simple, but very nice criteria for failure. He said, draw the elastic compression line, which essentially means take the pile with its characteristic as if it's freestanding and loaded, like it would be a column. Draw this elastic compression line that you learned first class in civil engineering, and then get an offset, and the offset is the diameter of the pile divided by 120 plus 0.15 inch. Well, where did he take it from? The D over 120 comes from his assumption that that will be the displacement that is required to mobilize the end bearing, and the 0.15 inch comes the displacement for developing local friction, which is independent on size. Well, we can check if he is right or wrong, but before that, just put scale in mind. In engineering of today, with all the numbers that's running, the most important thing is to have scale in mind. And the scale here, that if we have 1 foot pile, we are talking about offset alone of 1/4 of an inch. If we have a 3 foot pile, we are talking about 1/2 inch, and 72 inch pile, we are talking about offset of 3/4 of an inch. That becomes sizable, and that's addition to that, we have the shortening of the freestanding column. These are test results that we ran, quite sophisticated, on a testing device, which we call a dual friction apparatus. And the aim of that testing device was to measure the friction between materials and a solid surface, where we control the surface roughness, and more than that, we can check the friction as opposed to direct shear, where we have end effect, and we don't know that. I'll show you in a second. To check the friction in undisturbed mode, as if it is actually a pile shaft that does not have any restrictions above and beyond what is the friction. What you see, or you can see very clearly, is that we have on the vertical axis the friction angle, the interfacial friction angle. The horizontal axis is the displacement in millimeters, and the streak graph relates to a smooth surface, an intermediate surface, which essentially is sandblasted steel, and a very rough surface that guarantees that the friction will be developing fully in the soil for the shear strength of the soil. Just as a side note, pay attention that if it is only the front of the machine, like a direct shear, this would be the result, and therefore it doesn't represent correctly what's going on. But that's not the point. The point is that if you pass a line of 0.15 inch, or about 3.8 millimeters, as suggested by Davisson, you can see that it's a good criteria where the full friction is being developed, and it is a solid suggestion that he had. Later on, I'll show that this is good only for piles that do develop straight typical friction, like driven piles. It's not necessarily appropriate for drilled foundation, and we explain why. We have all these criteria that hopefully you know: Davisson, shape of curve, displacement, and also maybe to mention De Beer that developed it actually for shallow foundation, where he suggests to draw the load displacement on a log-log scale. Somebody told you before about the square root or the square. That's the same situation in engineering. You draw everything on a log-log scale, and it looks reasonable. The idea is really behind it is to change the regime. Where does the regime change in the loading from more or less elastic to plastic, and then asymptotic of those lines is the failure, and it's certainly a good criteria for shallow foundations. We use it all the time. Well, when we started working on those things, we collected a large database. That's an old database, Some people refer to it as the FHWA. It's not. FHWA helps us. And we took all these cases, digitized all the load displacement, analyzed them, first of all, plotted them in a systematic way, just I showed you, and analyzed them systematically. That was essentially the beginning of systematic calibration for the LRFD that came after that. And what we did there was we had to evaluate at the end of the day what is the capacity, which is what is in this yellow row right here. And then compare each one of the methods to what we would consider the true capacity here. How did we define the true capacity? I can explain, but in short, it is the average of the viable solutions plus the shape of curve which has some judgment in it. And then we got the distribution of all these hundreds of cases of what is the capacity of a pile based on different criteria. As you know, when you use normal distribution based on mean and standard deviation, you get a nice curve, but it does not necessarily represent correctly the data. So when you look on the data, you really need to look on an histogram diagram of the frequency of the result, and this is Davisson, which compared the actual frequency to the normal distribution, or more accurately should be the log normal distribution that you see there. And you can see that it worked fantastic. It actually works very well, and that should have been the the method for us to analyze driven pile. So the failure of the Davisson failure criteria is the most objective, reasonable, unique, provide a good result for the analysis of driven foundations. However, bear in mind this distribution. It didn't work for all the piles. Within one standard deviation, essentially took it as 0.15 up and down from the actual result. When I say 0.15, it means the ratio between what Davisson criteria would give to what we thought is the actual capacity of the pile independently and so on. And then we recommended, and later on, we compared all the flow tests that we had results, dynamic, static, no matter what, to that criterion, and that's what we used, and most people, I think, adopted Davisson criteria. We did the same for drilled foundation. There is no need to go here. We checked it on Davisson, De Beer, shape of curve, and what's called the FHWA method, which is O'Neill's method. And again, we got distribution and so on. Davisson did not work well for drilled foundation, and you can see that. So if you use Davisson failure criterion for drilled foundation, there is an inherent problem. We can explain it later in the lecture. What did we use? We used FHWA or O'Neill's 0.05B as the displacement. The take from this few slides that I showed you is that there is no unique failure. You need to examine load displacement in a consistent scale, as well as I'll show soon displacement with time versus load with time. For driven pile, use Davisson failure criterion. It's systematic. There are a couple of exceptions, and I'll talk about them. And for drill foundation, use Mike O'Neill's criterion of 5% of the diameter is the displacement for which you will assign the failure. I did not touch it at all, but for rock socket, we use Fred Kalhawi. Those of you that are familiar with our NCHRB 651 can look at that when we check foundation on fault and the bases, and Fred's criterion works the best. So let's look at a couple of related issues. First of all, what did I mean by loading and settlement with time as a result of the load test? What is the effect of rate of static loading with inertia? The settlement of a single pile and a pile group, and a size effect. And we'll do a few slides. If you already collect data, instead of just having the data looked into the load displacement, which we just showed and doing, you can have the same data drawn where you're looking on the load with time and the displacement with time. So the blue area here gives you the applied load versus time, and the green area gives you the displacement with time, and essentially the axes are combined. It gives you an ample of information just to look at it. You can, by the load with time, especially on slow maintained or quick tests in which you have periods that you're holding the load, you can see very clearly where creep starts and you're essentially not able to hold the load. the same on the load and the displacement. The look on those things is exceptionally rewarding and give you a lot of insight. Well, in today's time, when you collect the data, it doesn't really take much, and you get a lot of information. Let's look on the rate of static loading. I'm not talking about dynamic here. There is no inertia effect. If you just look on static loading, on the typical static, the one that used to be the most common, the slow maintained load test that would take certainly more than a day. This is the blue line with the gradual and the holding time of 12 hours and so on. Then we have the short duration, which usually takes us somewhere in the order of 6 to 8 hours. And then we have a quick load test. And the question is there a difference in the pile behavior on those static or quasi-static loading? It's not dynamic. And what we did, we ran 2 pile load tests. Actually, we ran much more, and I'll show you in a second, in which we compared 3 testing methods on the same pile. On the right side is a concrete-driven pile. On the left side is a steel pile. And what you see are 3 results. The blue line is the slow maintained test. That test took more than a day. The regular slow maintained with the 12 hours and so on. The red line is a short duration, which was something in the order of 6 to 8 hours test. And what you see in the green is actually a test that we worked in collaboration, and I'll speak about in a second, and we developed, in which you have a very quick load test. You essentially apply 3 cycles of 15 minutes each of loading. You come to failure, you unload, you reload. Each one of these green cycles is about 15 minutes. The whole test takes 45 minutes. You don't see a really big difference between them. There is no difference between them. As a matter of fact, the cyclic tests have a big advantage as far as failure goes. And I can't go into that much deeper, but if you look here in this location, for example, the point that you have the load-unload interception is exactly where you would define the failure. And it's on the books in the Massachusetts Highway Department. I'm not so sure how many people use it, but the rate effect within the quasi-static behavior really is of no importance unless you are especially interested in the creep. As a matter of fact, I think that we have something holding us. We actually collaborated, that's the next slide, with the Ukrainian institution at the time of the Soviet Union. And I just want to take a point here where DFI is a very important institution. There was no collusion whatsoever. And our name was deducted from Waller's report, and there is no problem. So we collaborated. That was the time, actually, under the Soviet Union, that there was a lot of fundamental research, which was really good. And these are 75 pile cases where you had loading of slow maintained load versus a quick static cyclic that I just showed you, and up to very large, relatively very large capacities. And it shows you that there is no difference between the two, and as a result, you can run load tests with the relatively very fast duration and have the same result as long as you come to failure. Well, let's move now to settlement. What's going on with the settlement of a single pile and pile group? In general, in our practice, we tend to think that once you design a pile for a design load, you don't have an issue with the settlement. We collected a lot of data about that. And what you see here is essentially 5 groups of different piles, H piles, closed-ended, open-ended, drill shaft, and so on. So each one of these crosses represent a mean, standard deviation, and all the extreme for one group of piles in which we check the settlement of the pile under the design load. The central red cross combines all the data of 105 piles. And what you see that essentially the typical pile under the design load goes all the way up the design load up to more than 2,000 kilos, more than 100 tons, 1,000 tons. Essentially is maintained within about 1/4 of an inch or less than that. So we really, our common practice is once we set up a capacity and we go to a design load, which is, if we have a load test, half of the capacity typically, we have a very limited settlement and we are pretty fine. What I want to add is on the top here, this particular result. This was collected by Modigliani, and there are 63 tests there, or results of tests, but actually they are part of groups. So it represents 16,000 piles. As a result of that, the load of the average is very high. You can see it's like close to 2,500 kits. However, the average settlement is about the same. It's smaller than 0.2 inches. If we are looking on or interested in what happened under the ultimate load or maximum load if you don't get to that, this is the result for that. Here the average resistance doubled with more than 1,000 kips, and the settlement went to 3 times. So on the average, those piles moved about 3/4 of an inch as a settlement. I don't want to go into prediction. We did that. The elastic analysis really don't work. A simple equation does a good job in predicting those things. The next one that you would like to look is what happens if we have a group of piles. Definitely in driven foundation, we work only in groups, and that's the ratio between a settlement of a group of piles to a single pile as a function of the spacing. So typical spacing will be 3 diameters, and that's about 1.5 times. If we go to smaller spacing, which is 2 diameters, which essentially we don't do usually, we are coming to a large increase in the displacement. If we go more than 3 diameters to 4 to 6 diameters, we are talking about 1.25 times the single pile, the settlement of the group. The last one was size effect. I don't show much of a data, but I'll explain what I did and why. There was a claim the Davisson criterion is not good for large piles, and we have to increase the tip displacement or the ratio instead of B over 120 to B over 30, and that was the claim. And we decided to check it independently, and we examined it by looking on a database in which we showed the bias of the method if it changes with the diameter, and then took separate group of 30 large piles that were over 2 feet in diameter and checked, does the criterion really changes if a failure goes there? There is no justification for that. Davisson criterion worked fine for large piles and small piles, and the criterion is good. There is no need for modification. So the size effect was not really anything that we got. Well, we are coming to alternative methods of testing. So why should we use alternative methods of testing? Because the load test, the static load test, has major limitations, and you could see it in the presentation today. They did not run a static load test. I, as a matter of fact, started my career in 1979 measuring dynamic measurements with an analog PDA that not many people would know what it is, and measuring static load test on offshore piles full capacity. It's very expensive. There is no question that static load test up-down is very expensive. It's very time-consuming, and I'll show you in a second what you need to do if a certain phenomena is immediate to test right away. We're running small number of tests. If they cannot be representative if there is a large variability. Unfortunately, the current AASHTO specification took out our portion in which we connected number of testing to site variability and explain how do you get site variability as a number and what number of tests you should use. It's not there anymore, but that should have been there because that's part of the issue. How many tests you need according to the site variability. And then if you have a problem, let's say you drill the drill shaft and you want to test it, and then drill shaft, got screwed up. What do? You're ending up with one test that is not good because the foundation is good. So all these difficulties really gives us the limitation from up-down static load test. In most of the cases, we don't even come to failure. I remember when coming to the United States, I was interested, and I found out that only 8 states in the Union had a code that requires a static load test to failure. The majority requires twice the design load or a little bit above it. So if you don't get to the failure, you essentially don't learn too much because it's a proof test and not a load test. And of course, that's generic. You need additional effort of strain gauges and measurement in order to measure the distribution with depth. All right, let's touch on the Osterberg cell or the bi-directional cell, the STM, the new standard. And I'll just bring a few slides on here. We don't have the time, but I don't think that it's appropriate to give a lecture to the memory of Julie Osterberg without mentioning the Osterberg cell. So that's certainly the other alternative for a static load test, only that we are loading it from the bottom up instead of the up-down. His major innovation, I must admit, was essentially developing something that was consistent, good quality engineering. I knew before that people that were using flat jacks to measure drilled foundations, small ones, and it worked fine, but it was not the same. He really established a methodology that worked technically fine, does not require the reaction, and as a result of that, we are much more affordable. Of course, it has disadvantages too, but that was the biggest advantages to be able to load test, especially large elements like drilled foundation with a load test. Mostly we put it, as you know, on the bottom part, either if it's a rock on the real bottom or above it, and we run a test. I'll just show two examples which are non-traditional because otherwise we didn't get much out of it. It's repetitive. This is a Osterberg cell that we worked with load test, that sponsored the lecture, many, many years ago, and we actually mounted it on a driven pile, the bottom of a driven pile. And at that time we developed a 6-inch stroke, which was not the common design. It was a 100-foot pile, and why did we do that? Because we were interested in gain of capacity with time. Until you build the reaction and everything, most of your data is already gone. You essentially load the pile that already gained 3, 4, 5, 6 times of its capacity when the beginning of the driving. So we did that. That was our piles. There were 3 piles actually in the test. You see them on the left. The one that went all the way down is about 100 foot long. It's TP1, and where you have the red circle on the bottom is an Osterberg cell on a driven pile. I won't get into much into the study, but I'll just show the fact that we ran this test, and the measurement here is hours after beginning of driving, start of driving. That's so you can avoid the zero in the beginning, at the end of driving. And you can see that that pile had very little capacity. As a matter of fact, within the clay layers, there was no resistance whatsoever. It's beyond the lecture. But what I'll show you, what we gained out of it, is this gain of capacity with time, in which the first test was completed within 10 hours after the driving of the pile, and you can see the resistance. The resistance shows you here either in PSI on the right side or KPA on the left side, and it's minuscule. As a matter of fact, it was zero practically at the end of driving within the clay due to the high pore pressure that was developed. As time passes, each one of these circles was another Osterberg cell that we ran on the same pile over 2.5 years. What you see at the end of the process is the last Osterberg cell, and then the square is a top-down test, which essentially gave the same result. So this is one use that I'm sure is not a regular use, but you could think about what you can gain out of research from an instrument that can load the pile immediately after driving. The other one that I'll show is a recent test that was done with GRL in Israel. And what you see is the thermal integrity profiling of a bidirectional load test, and there are 2 issues to take out of it. First of all, that you phenomenally can learn about the shape of your drill shaft exactly the way it's built. And that's a tremendous knowledge, well beyond CSL that gives you the integrity between the piles. On the right-hand side, you have all the tip analysis. You can see the bottom where the load is. But more interestingly, look at the shape of the pile. And that's not unusual, but for drilled foundation. And what does it mean? It means that when we load elements like this, we do not have a typical frictional behavior. We have in the areas where we have change in diameter, and that's actually nice. You know, in CFA, we can get much more than that. But we are talking about these areas, a relatively large change in diameter, which much more than asperities in a friction between solid and soil. That means that essentially you have another mechanism which more associated with end bearing of resistance here if it would have been top down. That is, as a result, when we checked those drilled foundations and came up with a what kind of interpretation for the load test would be appropriate, Davisson cannot work for that. Because the entire mechanism that we see in drilled foundation very commonly is not the typical friction. That also affects our dynamic test results. Very often we see all these results and people say, it doesn't mean anything, it's not good. Well, that's part of the issue that we have. That the friction is not the typical friction that we see. All right, the last few slides are associated with dynamic testing because there is no way I can avoid that, even though I missed the pic taken. And if you look on tests in general, just the concept of time scale in the test, and we used in that case the Kelvin-Voigt model, you can come up with what is the loading time of each one of the tests, starting from a dynamic test in impact to statnamic test, then Fundex, which I assume most of you are not familiar with. It's those testing with a big spring, which is a very long wave, to what you would call static, which is just as it is. And the question is, does it really look like that in real life? Here you have one of our tests on 14-inch square pipe pile, a concrete pile, and you can see here the actual measurement from a dynamic wave to a statnamic wave test that we ran, to static cyclic, this one that takes very fast, 15 minutes, all to a short duration. Didn't put here the slow maintain because the scale will get out to the next slide. And you can see, now there's a very importance to it. It's not only a nice academic. What it means is, and I can't again go into that, that if we measure what's so-called wavelengths, the whole concept was developed by Holliman, you essentially measure under the dynamic effect, what's the length of the wave that you send relatively to the distance that it has to go down and up. The shorter wavelengths that you have, the more or the better you can analyze the interaction of the pile and the soil. So every one of them has advantages, disadvantages, but bearing in mind when people give you analysis of a driven pile with CAPRAP and others, that there are advantages and disadvantages. Just a couple of words on the basic principle of the dynamic testing. Essentially, we are trying to get a static capacity out of the dynamic behavior of the pile during driving. Why do we can do it? Because in principle, if we run a driven pile or impact of a drilled foundation and that unit moved, we essentially under each blow conducted a very fast load test. So there is a very well justified basis to the fact that we'll take the dynamic results under a single blow, looking on it as a load test. It is a quick load test, as long as it penetrated. You had a load test, or if not, how long? Well, what is the method of analysis that we are using? We are using the one-dimensional wave equation, and here comes the pitfall. The one-dimensional wave equation was developed on the basis of wave propagation in a slender, uniform element. If you want to move from three-dimensional to one-dimensional, you have to make the simplification that the element is uniform and slender. Okay, that's fine. That happens with most driven piles. That will be the case. However, it does not consider an inertia effect, and in many of our analyses, we violate it. And actually, thanks to the lecturer before me, I can refer to it. Before we refer to it, let's look on the regular piles. How good is the analysis? The analysis is fantastic. If you run driven piles and you run CAPRAP, when you have either the beginning of free strike, meaning either you have a material that doesn't gain capacity of time, or if it gains capacity of time, you took it into consideration, you have excellent results. We use the same static capacity for those piles that we had, and the results show here for 162 cases that the mean is 1.158, 116. What does it mean? That we are under-predicting. This is the capacity of the pile based on CAPRAP divided by the actual load test. So if the number is greater than 1, we have a certain 15% extra. It's interesting that the first lecturer here today mentioned the 50%, but it's a small sample. It's mostly just incidental. So it works very well. In drill shaft that can be mobilized, it actually works even better because you don't have an inertia effect at all. You did not move the soil when you drove the pile, you drilled it, and we have done since then more comparisons between drilled foundations and capacity on signal matching, and it really works well. Well, so what are the not so good news? We have encounters. When do we encounter difficulties? When our assumptions of the theory are violated. That's why it's so critical to understand what you're doing. Where do we encounter this? First lecture talked about plug piles. We solved it by essentially another analysis where we do signal matching with different models for the plug and the interaction between them. As I said, I did not show it, and I wanted to leave things simple. But here is an example, and you had it earlier today, where the interaction between the soil and the pile when it's plugged, not when it's unplugged. When it's unplugged, it's like soil outside, creates a situation that we violate the basic one-dimensional wave equation. As a result, we have lower capacity. There are many ways to do it. What happens? We have non-uniform drilled foundation. We heard it from the second lecture with the pipes and the variation. We worked for years on that, and we did analysis. What happened? We have large soil inertia. You have easy driving. There are large movements. We actually measured it in collaboration with the Delft in Holland to measure what is the acceleration of the soil that moves when you drive the pile. Somebody talked here about liquefaction. We're ahead of the pile. That's exactly the case. So that will all affect your results and essentially create an inaccuracy. Well, capacity change in time is inevitable if you try to get capacity from a dynamic test and later the pile gain capacity or loses capacity. Well, it reflects only the time of the test, and you should be aware of that. All right, I think we came to a conclusion, and you went to a long ride. Static up, regarding static up-down loading, this is a benchmark for the test. You want it, get the best out of it. Examine standard load settlement scale, representation. Don't just throw it in every scale that you want because you lose a lot of the data. Use Davisson criteria for driven piles. No question about that, works well. Use the O'Neill's criterion, the 5% of the diameter for drilled foundations. Examine load versus time and settlement versus time in addition to the load displacement to gain insights. Settlement is under control for typical loading, and sizes serviceability is of concern only for really large elements, and you have to consider what is the serviceability when you are dealing with piles of 6 foot and 5 feet and 8 feet and so on, because that will play into the design. In dynamic testing, the reliable accuracy in testing of driven pile and drilled shaft, we definitely gain that, and be aware of limitation once conditions of the basic assumptions are violated. Large soil inertia in easy driving, very easy driving, plugging of piles, non-uniform drill shafts, and capacity change with time. I want to just say a few acknowledgments beside the people that invited me here. You work on this over the years, it's 40 years, from the people that were your mentors, and I was very lucky on that in the Israel Institute of Technology. I worked with a guy by the name of George Zeitlin that was a phenomenal graduate of MIT in 1939 that served in the Second World War for 5 years, and including D-Date, and had tremendous experience. So I was also fortunate enough to have wonderful students when I moved to UMass Lowell completely incidentally, and I stayed there because I had wonderful students over the years that helped me and the support of many research projects. If you have time, go to see the Chihuly Museum. That's a picture from there. And thank you very much for the attention and the lecture. If you have any question and we have time, I'll be happy to answer.
Samuel, thank you very much for decades of enlightenment.
Thank you.
Thank you.
Holy cow. Sure. Okay, we got this.
And thanks very much on behalf of the DFI.